This video is about the mass spring system. A simple mass spring system looks like this. Here we will work with a horizontal mass spring system so that we don't have to worry about the gravitational force that acts on the system. In addition, we will ignore air resistance and friction. Let's assume that the mass in this diagram is in the equilibrium position, which means that the spring is neither compressed nor extended. From this position, we can either compress or extend the spring. When the spring is released, the system oscillates with simple harmonic motion. As we learned in subtopic 4.1, when an object oscillates with simple harmonic motion, a restoring force acts on the object, which always points towards the equilibrium position. When we discussed elastic potential energy in subtopic 2.3, we learned about Hooke's law that can be applied for a spring. This law states that F is equal to K times delta X, where F is the spring force, K is the spring constant, and delta X is the compression or the extension of the spring. When a mass spring system oscillates with simple harmonic motion, the restoring force is equal to the spring force, therefore it is equal to negative K times X. X, the displacement, is basically equal to delta X, the compression or the extension of the spring, and the negative sign is included in the equation to show that the force and the displacement point in opposite directions. Let's work with this equation to derive the time period formula for the mass spring system. Based on Newton's second law, we can replace F by ma, where m is the mass of the object attached to the spring and a is its acceleration, and this is equal to negative k times x. When we divide by m, we get that a is equal to negative k over m multiplied by x. In the second video of this subtopic, we learned that a is equal to negative omega squared x, where omega is angular frequency. Comparing this equation with the one above, we can see that k over m is equal to omega squared, and when we equate these two values and take the square root, we get that omega is equal to k over m under the square root. In the first video of this subtopic, we learned that omega is equal to 2 pi over t, where t is the time period. After equating the right-hand side of these equations and rearranging for t, we get that t is equal to 2 pi divided by k over m under the square root. Dividing by a fraction is the same as multiplying by its reciprocal, so the division by k over m under the square root can be replaced with a multiplication by m over k under the square root. This leads us to the formula that you can find in the IB Physics data booklet. And here are the variables that are present in this formula. Even though we have derived this formula here to help you understand the concepts behind it better, you don't need to know this derivation for your IB Physics exams. You just have to be able to apply this formula on problems. This completes our discussion of the mass spring system. In the next video, we'll learn about energy changes in simple harmonic motion.